Okay.
Just this. Yeah, you can see this a second. Yeah. No, no, you do not.
Give it another percent. Give it away.
Yeah, that's
Okay, should we start?
Yeah.
Is this running then, or where did
We have to wait for Sharif.
Sharif go? Okay. Okay, so let's launch into the next topic, which is nonlinear time history analysis. I'm going to keep it at a fairly high level, but just talk about some of the important things that you need to be mindful of. So if we look at the general equation of motion, we have the mu dot plus cu dot plus the restoring force, and that's equal to the mass times the ground acceleration or the applied force. When we're running the linear analysis, the Fs is simply equal to the stiffness times the displacement. Okay, because it's still in the linear range. When we have the structure going into the nonlinear range, this Fs, which is the restoring force, is a function of the displacement and perhaps the velocity as well. The other thing that can happen is you can also have nonlinear damping. We don't usually deal with that, but there is a possibility that you could have nonlinear damping. We will ignore that for this conversation. But really the only difference is that instead of having your restoring force as just the stiffness times the displacement, it's now a function of your it's no longer a linear. There's no longer linear relationship between stiffness and displacement. So it really depends on the loading history and how you've got to this point, what has happened in the past, what is the history. This is just one example of an elastoplastic system of restoring force. It goes up at one slope, then it goes plastic, then it comes back down, goes plastic on the other side. So you can't run a linear analysis on this, and we have to do nonlinear time history analysis. The thing with nonlinear time history analysis is that for the most part, we have to do a coupled analysis. We've got to do the basic integration of these equations. There's really no way around it. So when we were doing the response spectrum, because it was all linear, we could do other things. We weren't directly integrating these equations. In this case, for the most part, except for maybe when we do the finite or the fast nonlinear analysis, what I might touch upon in a bit, you really have to do this. Now, your UG or your forcing function is usually numerically defined. So the analysis has to be done in a numerical fashion. There are no closed form solutions available for this type of problem. Some of the procedures that you'll find, so these are time stepping procedures. Your accelerations, the earthquake accelerations are going to be digitized, their values at very small intervals, perhaps a thousandth of a second or 500th of a second, and you step through the analysis. You've got your acceleration coming into your system at very, very small intervals, and you solve for each time step, and then you march forward in time. Some of the methods are the central difference method or the Newmark's method, the Wilson's theta method. If you want to read about that, you can have a look at, there's a lot of background material. You can look at Chopra's book or Ed Wilson's book. Dr. Wilson has been a pioneer. He's done lots of work there. And a lot of his stuff has been codified. He's codified a lot of stuff himself. So. Now, when we look at these solution algorithms, you can broadly categorize them as explicit methods and implicit methods. The big difference is really how they operate. With the explicit methods, you only need to know the solution for the previous time step, okay? And you're always marching forward. So if you know the solution at time I, you can use that to find out the solution at time I+1. So for your next step, you just need to know the previous step. That's why they're called explicit methods. The implicit methods, you cannot directly determine the next time step value. Okay? And if you go into some of those, you can see that I+1 shows up on both sides of the equation. Nevertheless, there are ways to solve it. I'm not going to go into it, but go to Chopra's book, look at chapter 5, and there are very nice formulations that you can pick up very quickly. You can even program those in Excel, or I guess you guys are way more bright than I am in terms of programming and everything else. I tried to do a little bit in Excel many years ago. So MATLAB or anything else, you can do those. The other thing I want to talk about is stability. Some of these are conditionally stable and some of these are unconditionally stable. For conditional stability, the time step has to be short enough, otherwise your solution is just going to diverge. But usually we don't have to worry about it for earthquake loading because the time step is already so small that your stability is mostly satisfied. The linear acceleration method, which is Newmark's method with the gamma and beta values of 1/2 and 1/6, is stable only if the time step divided by the natural period of the structure is less than 0.55. The central difference method is stable if the same value is less than 1/pi. The average acceleration method, which is again Newmark's method but different gamma and beta values, is unconditionally stable. Okay, so unconditional stability is that you will have a bounded solution no matter what the time step is. Whereas conditional stability, you have to account for the time step. It has to be small enough. But as I said, the stability criteria are not too restrictive from ground response analysis because the values are already given at 0.01, 0.005 seconds. So those are already very small intervals. So this is just one example of the central difference method. So you have your initial calculations that don't change, and then you can calculate the values for the next time step. I just pulled those out just to show you. This is the average acceleration, and this is linear acceleration. So you assume that your acceleration between the 2 points is the average, and you formulate it based on that. Whereas here you say that the change is happening in a linear fashion. Okay, so the most general approach is the step-by-step integration of coupled motions of motion. The beauty of the nonlinear time history analysis is it combines the demand and capacity sides together. Okay, so remember how when we're doing a response spectrum, we're getting the demand, we're doing a pushover, that's more of a capacity side of things. So then you compare the two separately, and then you have to figure out if you've met the performance or not. When we run the nonlinear time history analysis with all the material models in there, degradation, what have you, real-time analysis, no need to do any kind of statistical combinations, you are going to get the final picture. The demand and capacity are now intertwined. So right away you see your displacement is this much, your strain is this much, your rotations are this much, so you can directly compare it. There's no more processing in terms of, okay, I'm going to now divide this rotation by that much. It's just happening, or my displacement is this, and now I'm working backwards or forwards, so it just happens right away. There is this fast nonlinear analysis, which is a nonlinear modal analysis using Ritz vectors. Usually we use the natural modes for the basis of modal analysis, but you can also use Ritz vectors to come up with your modal analysis. And I think Dr. Ed Wilson came up with this fast nonlinear analysis technique. So if you have concentrated plasticities in only a few elements, there's a formulation. If you go to Google and you search for it, you'll find some stuff on it. There's a description, a nice paper by Dr. Ed Wilson that I think you can get from CSI's website. Midas also has a fair bit of description on it, but it's really suitable when you have plasticity in only a few elements, and you already know where that's going to happen. So one example is where you're going to go and base isolate your structure, and you know exactly that those are the points where you're going to put your base isolation bearings, and everything else you're going to capacity protect, and it's not going to go inelastic. Then you can use the the fast nonlinear analysis. It's a type of a modal analysis. It's not working with the direct integration of the coupled equations, but that's what we usually do. This is something I want to bring to everyone's attention. There is something called the backbone curve. Hopefully everybody knows about it. It's a force displacement capacity boundary, and when you're running your, say, some you guys are doing some testing, you go back and forth, and you can see that you start to degrade. Your hysteresis loops can start to degrade. So if you were to just push it once, you may get this backbone curve, but then if you cycle it a lot, it might actually be degraded. So in a sense, when you're running the nonlinear time history analysis and you know that the earthquake is going to cycle your structure quite a bit, you should be putting in the degraded curve, not the monotonic curve. The thing is that your force can never exceed your boundary, because it's just physically impossible. So as soon as it hits that point, then the force gets capped, and it becomes now it turns into a nonlinear. It is a nonlinear problem, but you have to tell your program to use that. And I think that's what we're doing. Even when we were looking at the pushover with some degraded capacity, the program will never give you more than what that level corresponds to. So it's important to think of that. There are lots of different hysteretic rules. The elastoplastic, this is coming out of Dr. Priestley and Calvi and Kowalski's book from 2007. You can look at a lot of these different models. This one is quite interesting. If people, I think Chi has been doing some work on some models that incorporate the flag model with pre-stressing steel in there. So this goes up and then it forms a bit of a loop up there and then comes back. It's good, even though it doesn't have a lot of energy dissipation, but it's good to bring your structure back to the normal position of equilibrium. You can have Takeda models that are more for concrete. Steel is more elastoplastic. You can also have gapping elements for soil. So when we're doing these nonlinear time history analyses, we have to really understand and have an idea of how the material is going to behave and think about what material models we want to use. This, I hope everybody has seen a modified Newton-Raphson or a Newton-Raphson iteration when you're doing a nonlinear analysis. You go with an initial stiffness and you figure out that there is a residual in your force vector, and equilibrium is not satisfied, and you correct for it. And we talked about this a little bit yesterday relative to the PY curves. Is the same idea. So nonlinear time history analysis will help us predict some lateral dynamic instability if we incorporate strength and stiffness degradation appropriately. Okay, so if we've modeled rebar rupture, if we've modeled buckling, if we've modeled concrete crushing, all of that is in there, and we can capture the degradation then. And also perhaps if geometric nonlinearity is an issue, if you run it, it might the analysis might blow up at some point. And that tells you that your structure has basically failed, it's collapsed. Be careful, because it might come around as a result of just numerical instability. Okay, so you have to be a bit careful in terms of figuring out if it's skill or if it's just spurious because of some modeling issues. But it is able to capture that. So in terms of aftershocks, the best thing is to run nonlinear time history analysis. So you have your main shock, you input your motion, and then you give it a fair bit of time of zeros, so that the structure then goes back to static equilibrium. It stops vibrating, and then you can hit it with the second shock. Okay, and at the end of the day, if you've incorporated all your degradation mechanisms and all your parameters appropriately, you should be able to see after both events where your structure is sitting. Okay. Again, structural performance under live load after an earthquake. I touched upon this a little bit. It can be more realistically demonstrated. So if you run your time history and you put a bunch of zeros, you can figure out the residual displacement or drift after the end of the earthquake. Now you can put your traffic on it because it will have the drift, it will have those moments locked in. And if you run a nonlinear analysis starting from that stress state, then you're able to see if you will be able to put the live load on it or not, or if you can't take it or not. As we were talking about before the break, the only way to do it is really to fudge it with just a pushover analysis, and I elaborated on that a little bit. Okay, so moving on. I want to talk a little bit about damping and performance demonstrations and mean response quantities. We might just talk about the design example. We can, with this again, just going ahead with some of the advantages and general applicability. You can capture better multi-directional response quantification, so you can put the 2 time histories or the 3 time histories simultaneously, and the results you get are going to be in real time. There's no need, as I was saying, to do any kind of combinations. You can quantify your hysteretic and energy dissipation. You can look at your strength and stiffness degradation, which is very important, especially for poorly detailed structures. So when you're looking at structures that need to be retrofitted, it becomes all the more important that we get a handle on it. Usually response spectra will give you, I don't want to say they're always conservative, but a lot of the times you find that when you run the time history analysis, your demands come down a little bit. Okay, now in terms of other analysis, like if you've got dampers and isolation devices, it's probably the best to use the nonlinear time history analysis. And if you look at the code under certain circumstances, you can use a modal analysis. You modify your response spectrum based on your isolation devices, and you can come up with damping in your isolation devices that may be up to 30% to account for that fact, the fact that these are energy dissipating mechanisms. But with outside of those very narrow bounds, the code forces you to run a nonlinear time history analysis and not just do this based on pushovers and modal analysis. You're looking at foundation rocking or joint opening and closing, soil nonlinearities, lateral spreading due to liquefaction. A lot of that can be captured a lot better with nonlinear time history analysis. The one thing I want to point out, though, from a practical point of view is if you've got all these nonlinearities going on, your runs might become very, very long and your results might become convoluted. So if you have 5 different sources of nonlinearity, you really need to pay attention. You might want to just start with 1 or 2 sources of nonlinearity to understand the effect of those on the structure first, before you go incorporating joint opening and joint cracking and plastic hinges and soil degradation and rebar and concrete degradation. So take it as one step at a time. And a lot of the times, the way to circumvent this is when you're doing new design, you are going to detail those things so that a lot of those issues just do not appear. Those things are suppressed. However, when we're looking at older structures, it becomes more meaningful to account for a lot of those things. But if you're finding early on that those deficiencies are extreme, then again, running a nonlinear time history analysis with the nth degree of precision is not very meaningful because you are going to see failure. Then you're better off thinking about how you're going to retrofit it. Okay, so once you've understood your failure mechanisms and their hierarchy, the hierarchy is very important. Is it going to be joint shear that's going to come in first? Is it going to be the foundation that's going to fail first? Is it going to be column shear that's going to really be a problem? Then you start to think about the solution to that problem. Okay, and now to demonstrate your performance after you've retrofitted it is a lot better. And now the time history may be a lot more meaningful. So you've got to hone in or zone in, focus on those problems and not just keep running analyses that don't give you a lot of value. Sometimes the deficiencies are so out in the open that you might not even do an analysis on the as-built structure. Okay? There are typical detailing deficiencies that people know about, and if you see lap splices in your plastic hang zone, if you see your rebars are curtailed all over the place, if you see your shear reinforcement is, 10 Ms at 400 mil, there is no real reason to say, oh, I'm going to go run a shear model on it. I know a 10 Ms at 400 or 15 Ms at 300 is just not going to work. So move on and do something more meaningful. Lateral spreading, FLAC is a finite difference software. It's used a lot on the soil side of things. Liquefaction is a very complicated phenomenon. I'll touch on it in a very simple manner in a little bit. But you can do coupled or uncoupled analysis. Uncoupled is when you just have the soil and you run and you see how much the soil is moving. And then in a separate analysis where you have the structure, you go and you impose those soil deformations onto your structure. But what really happens in real life, it's a bit of a repetitive sentence, but what happens actually is the soil behavior changes. So the piles and the soil interact with each other. So when you're running an uncoupled analysis under free field conditions, you get one answer. The soil might be moving 500 mils. But now if you run it with the piles, it may be 400 mils or maybe a meter, maybe 100 millimeters. So it's when you're really trying to focus on the problem, focus in on the issue. Sometimes we run coupled analysis, but even today with all the computer power, those models can run forever. And we really have to, I've been involved in one or two where I had to collaborate with the geotechnical engineer. They were running the FLAC analysis, and we couldn't have them build the whole bridge in this 3D space with the software. They told us they were going to be running it for weeks. So we had to lump column properties and stiffnesses and strengths together and give them a single element for a multi-column vent, etc. Just to get some sort of coupled analysis going and get some meaningful results. Then we had to come out again and use your normal structural software to impose those demands. And then the whole idea is that you detail it properly so that if it's moving, the soil is moving half a meter or a meter, you're able to take that. Okay. So the current requirements are more onerous than S606, and they're going to stay the same in S619. Back in the day, we had to use 5 spectrally matched time histories. Now we have to use at least 11. We cannot have more than 2 sets of ground motion that are selected from a given historical earthquake. So out of the 11, you can't just pick Loma Prieta and use 5 Loma Prieta records. They want variability in your records. For design purposes, we need mean response quantities. So it's not like the one value out of the 11 that's high. We have to go with the mean response quantities. If your site is within 10 kilometers of an active known fault, then we have to do specific vertical time history records. And we can't use the 2/3 or whatever. Okay, so this is, I want to talk a little bit about the damping formulation. And it still is there's a lot of research being done on damping for nonlinear time history analysis. So when we're looking at multi-degree of freedom time history analysis, and we look at direct integration, our damping matrix C has to be explicitly defined, and it's not easy to get those damping coefficients. This is a very important point. We have to realize that damping, the way we model it as a dash pot, which is a viscous damper, is not a property of the bridge system, of the structural system. It's just a mathematical formulation to put some damping into your system. The damping really comes from opening and closing of the cracks, from non-structural elements, from all of that heat and friction that occur, because concrete is going to crack very early on. As we know, the F cracking is only about 0.4 root F prime C. So things start to go, even though we think they're linear, they're starting to have some nonlinearity very early on. So, viscous damping is a property of a fluid, not that of a structure, not of a solid thing. But for mathematical ease, it's a mathematical necessity. Okay. So one of the formulations, which is the Rayleigh formulation, is basically taking a formulation which accounts for mass and stiffness into account. And that, again, is a matter of convenience. So their form is the mass has a certain coefficient and the stiffness has a certain coefficient. So you can have them separate, but the Rayleigh formulation, if you were to look at this is your mass proportional damping versus your natural frequency. And this is your stiffness proportional damping versus your frequency. So neither two of them, one just keeps going up as your natural frequency goes up. The other one keeps coming down as the natural frequency goes up. So when you combine the two together, when you add the two together, you get this Rayleigh curve, which looks like this convex line. And that's what traditionally we use in time history analysis to model damping. So your damping coefficient comes out of that expression, A naught over 2 omega n plus A1 omega n over 2. That's your nth coefficient. Okay, so what we have to do based on this, and I'll go into it in a little bit more detail, is we've got to come up with the A naught and A1 to adjust the shape of the damping curve. Okay? Let's go here first. So let's see how we can do this. And I'll talk about the shortcoming as well. So for this Rayleigh damping, we have two periods that we anchor it to. Two modal periods that we anchor it to. And we have to decide what those two modal periods are going to be. So we run our modal analysis and we see which two modes are giving us the largest mass participation. And the hope is that those two modes are the most important modes. And we set our damping to 2% or 5% or 1%, whatever we think is reasonable for those two modes. Okay, so then this curve here is anchored to those to that value. So you see how the damping is changing. Okay, but it's at this point and at this point it's the same. So one modal period is over here, the second modal period is over there. And we play with the A naughts and A1s relative to the omega n's to make sure that at that period and this period, we're matching the damping appropriately. Everywhere else, you're under damping or over damping. So between these two periods, you're under damping. Okay, if 2% or 5% is this line, every mode that falls along here is going to be underdamped. And anything that falls out there is going to be overdamped. Okay? So that in itself is a bit of a shortcoming in that some of the higher modes or some of the earlier modes you might be underdamping or overdamping. So for structures where you can find one or two modes that capture most of the mass in terms of that dynamic mass contribution, you're going to be okay. Now, if your structure is behaving in a lot of different modes and each one has, 5, 10%, 10%, 15%, and you have 7 or 8, then you have to really think about it and see, okay, I might be underdamping here, but I'm only underdamping it by 2%, or I'm underdamping it by 5%, but here for a pretty large mode, I'm underdamping it or overdamping it by 20%. Now I'm going to start to get a response that's over damped or under damped. I'm going to get too large a displacement or too small a displacement. So this is one actual project that we worked on, and you can see here the UX and the UYs are the two horizontal directions, and this is the modal participation graph. So there is a big mode kicking in here. It goes from, so there's a small mode here, but then this is a big mode. There's a little bit here, and then this over here is a big mode here, okay? So we're anchoring to this mode, which is bringing in this much, and these two modes from the two directions are quite close, so we're anchoring here. So you can see my blue line now, which is my really damping curve, it's matching quite nicely here, and it's matching quite nicely here. So anything in between is a little bit underdamped, and anything before this and after this is overdamped. Okay, but you can see that the line is fitting quite nicely. It's not a huge difference. Now, if you had a mode sitting out here, okay, then you would be hugely over damping it, because we're trying to damp to 5%. This green line is the 5% line. Okay, if this mode were sitting here, you'd be damping it to 30%, not 5%. But then, of course, you would play with your A0s and A1s, and you would move this blue line, move this anchoring back so that you match that. So it can get a little bit tricky, but in something like this, which 2 or 3 periods are going to give you a lot of the modal mass participation, you're going to be okay. But be aware of this shortcoming. And this is all the stuff that I've just talked about. So you can easily do this. This is your first period that you've decided you want to anchor to. The second period, the frequency, the natural frequency, the circular frequency. And I want to damp both this and this to 5%. And that's my equation. Yes?
What happens to the vertical? Because the vertical one is...
Yeah, so the vertical, that's a good question. The vertical you can see is happening here. It's also pretty close. Right? If I were to draw this line, so this yellow is the UZ, right? So this is the big kick coming in. So if I were to draw the line here, you look at how far this is from 5%. It's not very far. The blue and the green are pretty close.
This is the, what if they were very much different?
Then that's a shortcoming for this model.
Check and see how much the vertical...
Then you'd have to go and maybe run it twice. One with a damping sort of that's targeting the vertical, and see if it's in fact giving you a lot of effect. So then you're in that gray zone of, okay, now my engineering judgment is going to kick in. I'm going to do different analyses and try and bound it. Okay? Yeah, so you can always use the first and the two. So the two equations you solve simultaneously, and you get your A0 and A1. In SAP, you can basically give it the values and or other softwares, and they'll just come up with the A0s and the A1s and run it. So this is, you've all seen those time histories, acceleration, velocity, displacement records. I'll let you just have a look at that. These are actual records we used on a project. The east-west component, north-south, and the vertical. And you can see that there's a bit of a difference. The vertical is hitting about 0.06 G. The horizontals are going to about 0.15. That's not always the case. If you're close, I've read that your vertical accelerations might actually reach or exceed your horizontal acceleration. So if you're in a near-field situation, that's when the vertical components become quite important. If you're in a far field situation, they're not all that big of a deal. Yes?
You use different motions when you're checking the damping? You check with one ground motion, or you...
No, that's not a ground motion. This is not This is not a ground motion issue. Yeah, this is just based on what my modal analysis, because we're assuming that those modes are going to be dominant in terms of the response when any time history comes in, because that's where most of the modal mass lies. Yeah. Okay, so this is just some language from the code. I think I've described it. So in the code right now, you can do matching two ways. One is the response spectrum matching, which you're putting some phases and all of that stuff in there. I think Norm Abrahamson has done a lot of work that I don't understand. It's beyond my expertise, but you have programs which can do spectral matching, seismosignal, seismomatch. They can all do that. The other one that the code lets you do within reason is linear scaling. Each one has pros and cons. When you do linear scaling, you're not going to get a very good match throughout the period range of your response spectrum. You're going to be over and you're going to be under. However, you will preserve the inherent signature of the earthquake, because you're not playing with the phases, you're not playing with the frequencies. When you do spectral matching, my understanding is that you're playing with frequencies and phases and all of that. So to some extent, you are changing the inherent signature of your earthquake. Okay, so those are two ways of doing it. This is just, how do you've got all that stuff, what are you going to do with it? I think plotting is a great thing. So you run the analysis, and this is showing is a time history response of an element, a column element. The axial load varies like that, the moment varies like that, and then down here is, so this is the transverse moment, this is the longitudinal moment, and up at the top is the axial load. And then you can see, okay, what are the bounds that I'm dealing with? So in this case, I'm dealing with about -1 meganewtons to about 6 or 6.5 meganewtons of axial load in my column. It's going up and down. My bending moment, this is sort of the strong motion part of it. I'm going from 5 meganewton meters to -5 meganewton meters, and longitudinally I'm between 3 to 4. So if you are just looking at tables, you'll tend to get lost. It becomes imperative that we start to plot things. Now, let's say that my performance criteria is basically essentially elastic. So I can plot my PM curve, where my M is my nominal capacity, nominal expected capacity. I can draw my PM curve, and in there I can plot all the axial force and bending moment points for the earthquake. If none of these points touch this envelope anywhere, you know that you've got your performance. So unless you do this, it's going to be very, very difficult to see if you've got a 40,000 point time history going on a big structure. Well, how do I make sense of it? You've got to get some outputs. You've got to start to look at things in this manner. This is just a graph of the longitudinal versus the transverse moments in that for 3 different sets in the column. So this is drawing real-time longitudinal transverse points and showing how it behaves. So you can see that it's going both positive and negative in terms of bending moment in both directions. You can also look at your hysteresis on your within your hinge, and you can see where at a given point where you are. You can also ask for maxima and minima. All the softwares have those facilities or those capabilities. They'll tell you what your maximum rotation was in during the whole time history, or you can plot it. Now, just one thought I wanna give you guys about the mean response. So let's say you run 11 time histories, and let's say one time history is say 30 seconds, another one is 40 seconds. So you've got 11 of those. The code says your design value is the mean response. Okay, so if I have the P's 40,000 points for one and M's 40,000 points corresponding, and I've got 11 of those. One thing I can do is I can just go and average all the P's at every given point, and then average all the M's at every given point. And then I can come up for every time instance, I can draw that. And I can say, yeah, this is my average. It's within this PM envelope. I'm done. Great. But if you think about it a little bit more, the time histories are very different, right? So the peak responses, again, might be happening at different points for each time history. Now, a little bit of an improvement you could do on that is you ignore the time component. So you don't pick the 5-second response in all of them and say, this is my P, my M, P, my P, and M, P, and M. So at 5 seconds, this is my average P, and this is my average M after I've averaged the 11 points. You can go with multiple small ranges. You can say for 100 kilonewton interval, 100, 200, 300, 400, 500, all the way to 5,000, for example, I've got 50 intervals. I'm going to go into each one of them and figure out what the corresponding moment is for that p-value. It may happen at different times, but that is a bit more meaningful because the P and M correlation is happening within the system. So now across the board, for say at 4,000 kilonewtons, I figure out when the P is 4,000 kilonewton in each one of those records, what the moment is. And I take the average of those M's and I come up with the average M. And that's what I plot. And so you can do that too, and you probably get something like this. I just want to show you a quick comparison of a response spectrum analysis and a time history analysis. This is an actual bridge that we worked on. It had a bit of a skew and a widening on the one side. The one thing I want to point out is if you look at the MX and the MYs from response spectrum analysis, you're looking at about 28 or 2900 for the X direction, 3700 for the Y direction. And when you're running your time history, your combined moment, your vector moment is about 2700. So that's a little bit lower at this point. Up here, you can see that again. So they're not too far off. There's a 15-20% difference, which is to be expected because this is real time and this is based on all those directional combinations and modal combinations, right? Up there, you're hitting a maximum of 3,900 and a time history of 4,000. So this is the kind of correlation you're going to get. You're never going to get the same answers, but you just want to check if you're in the ballpark in terms of just your linear stuff. This is an irregular bridge again, just highly curved ramp on the evergreen line. This was a straddle bend and then single column bends offset from each other. We did some preliminary work on it during bid design, and we found our D/C ratio for the drill shaft was 0.85, but pay attention to this. B11 is where we were overstressing it by a little bit, so 10% to 30% overstress. And everything else, P13 is getting a bit close, but the other ones are kind of not that close. So now we got the project. After we got the project, we ran it again. We got the same conclusions at that point. We ran the time history analysis, P13. So this is a PM, X, and Y curve that's plotted in 3 dimensions. And then within this, there's that trace of the PM demands. And so you can see that as long as it doesn't touch the cylinder anywhere, it's that you're meeting the performance. And here, so you see B11, which was a little bit over from the elastic dynamic analysis or response spectrum analysis. It was giving us about 10 to 30% overstress. It's still the highest when we run the time history, but it's just inside the PM curve. So the nonlinear time history analysis has kind of given us a better result in that we can demonstrate with this And because this is capturing everything in real time, that we're okay. Okay? Okay, so I'm going to skip this. This is really, if you want to look at this, this is a paper by Qi Zhang. This is based on his master's work. It really, the only thing I want to point out here is, look at these PY curves. Okay, so I'll point out a couple of things and I'll move on. This is for the Willingdon underpass. These are actual design data. As you're going deeper into the soil layers, your soil is becoming more strong and the PY curves are coming up. So these curves are going plastic at a much lower force value. These ones are coming up. So as you're getting deeper and deeper, coming up, but you can see that they hit that point and then they go plastic. This is a bit of a fictitious thing, right? Because the soil just yields and then it just goes, right? So you can model it to 400, 500 mils and get your results out. That's not it's just the force has to go elsewhere. So the geotech gives us the data in this sort of a format. So you see how for say 4 meter depth, there's a Y value and a P value. And that's what, when you plot it, that's what this looks like. Okay. So when you're doing a response spectrum analysis, you cannot put these values in there. You have to just give it a stiffness. And that becomes a bit of an automation exercise because for each spring, you've got to converge it. So you pick up one stiffness, you get the force in it, and you figure out if the force is above the plateau line, then you have to go and correct it. And so you have to do a few iterations. You've got to set up some spreadsheets. We've seen that. And that's what I was talking about. This was the model that he came up with. So here the deck was quite wide, so I think he did a grillage model rather than just a stick model to capture any of the torsional effects. And then so these are what we call extended pile vents. So the piles are in the ground. They're steel pipe piles that have reinforced concrete in them. And then as they come up and out of the surface, it's just the concrete that's continued up into the air, so that you don't see that, brown, greasy look of steel. But these are extended pile vents, and from out of the ground, you've got all the PY curves in there. So that's just a little bit of stuff. Now, we looked at 3 different cases, and then I'll take you directly to the results. We looked at force-based design for S606, force-based design for S614, and performance-based design for S614. And he did a bunch of pushovers and all of that, time histories. And what we found was we were not able to get to that 0.002. It was just impossible to get to that. So this is just showing you some material strain values. So at 475, we're hitting repairable, and then for 2475, we're extensive. We just couldn't make that work. So even with a lot of reinforcement in there, we weren't getting what we needed to get till we got to about 5.7% rebar, and then we barely met this minimal damage criterion for 475. But 6% rebar is not to be put into a system.
Did you put 5.1%?
No, that's not. No, this was designed beforehand, and then the code changed. So this was a study done that if we use the current code stipulations, where would we end up? And our thought was that we would end up with very practical rebar ratio, and we actually did. So it just proved our worry that not having a rebar yield at 475 is just very impractical. The other 2 criteria just holds in because their strain limits are quite relaxed. So I always like to give sort of a comparison here. I think that's a good question. So if you think about the seismicity of the Lower Mainland, Metro Vancouver, the difference between the 475 response spectrum and the 2475 response spectrum is anywhere from 70% to 100%. So your demand is going to increase by 1.7 to 2 times. Now you look at the capacity side of things, and according to the code, for 475, your rebar strain has to be below yielding, which is 0.002. And now compare that to extensive, which is what 2475 is tied to. The rebar allowable strain is 0.05. So for a factor of 2, for an increase in seismic demand of a factor of 2, the capacity increase that you're allowing is 25 times. So for an increase of 2 and a capacity increase of 25, that's never going to be your governing criterion. It's always going to be the first one. So I think that's where the fundamental issue was. That our 475 demands are not 25 times lower. They're like maybe 100% lower, right? So when you go to the next level, 975, you're already at 0.015, which even that is 7 times more than what you're allowing at 0.02. And from 475 to 975, you see an increase of 30 to 50%. So you can see right there that it's going to be an issue. So we did this study. This Dr. Allen's a master's student. We got that paper in the Canadian Journal of Civil Engineering, I think. So yeah, this was basically to prove that we were barking up the wrong tree there. Okay, so this is just the final thing. We did a little bit of, I talked about concrete degradation. You look at ADC 32, it has some equations that are based on your axial load ratio. You look at your Priestley and Dr. Priestley's book, and that's tied to your curvature ductility. Okay, so I think that's the most appropriate at this point. That's just because you run your pushover, you know exactly what curvature ductility you're at, and then he's got the graph, degradation graph tied to your curvature ductility, and you can see how much you need to reduce it by. Our code just has a blanket number, which says use your shear capacity formula, which has the beta and the theta, and it just says use a 45 degree for theta and 0.1 for beta, and it gives us it's quite conservative. I think now they're allowing other shear models to be used when the new code comes out. It's with the Chapter 8 Code Committee, so I'm not exactly sure, but when we were having our conversations, I think there was talk about using the model from 2007 that Dr. Priestley and Kowalski came up with. So just be mindful that you need to account for shear degradation when you need to. Okay, so I think I touched on this a little bit. Time history record selection and matching we'll maybe have a chat about. Hopefully people are aware that on the coast we have 3 different seismic sources. We have the shallow crustal events that happen within within the plate, like up high, 10-20 kilometers. The intraplate or the what we call them, the subcrustal events, and then we have the subduction event, which everybody talks about. If you ask me personally, and what I've seen over the years in terms of response spectra, living in Metro Vancouver, I'm more worried about a Christchurch type earthquake. Something that is maybe magnitude 6, shows up at 10 kilometers depth, right under Victoria or Vancouver. That worries me a lot more, especially when I look at the studies and we look at how far the Cascadia is from Vancouver. We're about 150 plus kilometers away. It's only, and when you look at the seismic hazard deaggregation, it's an issue with longer period structures. So when you're looking at 2 seconds, 3 seconds, so longer bridges, taller buildings, it's going to have more of an impact. But all the 1 or 2 story buildings, masonry buildings in Victoria that are, very non-ductile, those are going to get hit more by a shallow crustal event. That's my worry. Victoria will get hit more with subduction. We're farther away, there will be more attenuation. So personally, I feel like if we have a crustal event, it's going to do more damage. That's just my personal opinion. Touch wood, it doesn't happen, but if it ever happens, we'll see what falls out of it, but hopefully it doesn't. I want to give you a bit of an overview of how to set up a nonlinear time history analysis using a commercial software. So CSI Bridge, basically. You can read this. This is just some simple stuff. I talked about this already, linear scaling and spectral matching. So I've given you some excerpts from the code, and I have got permission from the code, the head, that I can share this sort of in this format. So I don't think there are any copyright issues. I've already talked to them. I think you guys are probably more up on where the resources are for getting earthquake records. They're NGA West and Peer and the KNet and KiKNet and all the Japanese, and I think there is a Mexican database that I still have to go look at, but that's just there are lots and lots of resources out there. I think Dr. Arman Vimanzadeh out of he's a colleague of Dr. Ventura. He's got a pretty large database. I was talking to him when we were at the CCEE. So if you guys are interested, maybe send him an email. He told me he would give me some of that stuff. I just haven't had time to touch base with him, but I think he's got a lot of those. I think Dr. Goda out of Western has a big database. So if you're so inclined, you can maybe send Dr. Katsuchiro Goda an email. So when we're doing a time history analysis, I'm not sure about other softwares, but you apply the dead load as a time history as well. That's just how this particular software works. It doesn't let you apply it as a static load. So how would you apply the dead load as a dynamic load and not get a lot of vibration and just cookie effects out of it? Because it's a very slow application. But we're going to apply it in a dynamic fashion. So one thought is that you really bump up your damping. You put 90% damping, right? So then it's just going to damp the dynamic response. Okay. Then you have the dead load. So this is the dead load time history. This is how I'm applying it. I take a function. I say the value of the dead load is 0 at time 0. And a full value, 1 at time 1. And then it just stays the same all the way to 20 seconds. It's still 1. Okay? That's how I do it. So I say use 0 initial conditions, use direct integration, use time history. That's what I've got. I've got proportional damping here. And when I go to proportional damping, I say my first modal period and point 1 and 1, they're at like 99% damped. They're just heavily damped. So you won't have any of those effects. So the reason why I'm not starting my time history all the way to 20, up to 20 seconds is I want any kind of damping or any kind of vibration to have just completely died out. And I'm putting in a lot of damping in there. So this is my time history in the X direction. You can read it through an Excel file. Of course, you're not going to put every number into it. There are ways of doing that, and those are software specific. This is the time history Y. Now this is where I apply the two simultaneously. So that's the time history X and Y. Okay, so this is a non-linear time history case. I'm not accounting for any geometric nonlinearity. I know my numbers are percentage of G, so I have factors of 9.81 in the 2 degrees of freedom, and I say continue from state at end of nonlinear case dead all plus, and the end of that nonlinear case happens at 20 seconds, right? So it just hits it quickly. It's huge damping. Now the force that's going to be in there after that, because it's all linear, is going to be unamplified, just bare dead load. And then I say, apply this from this stress state. I go with proportional damping, the Rayleigh damping that we talked about. And so these are the damping coefficients. I've done my analysis, my modal analysis beforehand, and I find out that the two periods I'm interested in are 2.3 seconds and 1 second. So I put 5% and 5%, it automatically comes up with those mass proportional and stiffness proportional coefficients, the A naught and 1, which I had shown you how to do that. So you just need to put this in, and with this, it just generates the whole curve, which helps it calculate the damping matrix. Okay, and I can use the Wilson theta method. There's Newmark, Wilson theta, collocation, Hilbert, Hughes, Taylor, etc., etc. Wilson theta, you go to maybe Chopra's book, 1.42 for theta is a good value. That's so you need to do a little bit of checking there. And then I say, okay, I'm going to look at my deformed shape. Show me my deformed shape for this time history, but show me an envelope. So you can imagine that this is going to look funny. Every node that's going to show up on this graph is at its maximum displacement, which is not going to be concurrent. So this node might be getting to its maximum at some point. This node is not going to be at its maximum at the same point. So sometimes people look at this and go like, what is going on here? Okay. Joint displacements, I can also ask for a maximum value, and it tells me that my joint 37 is transversely has moved 134 mils, or longitudinally it's moved that much, transversely it's 100, vertically it's about 25. And then it also gives me the rotations. This is another little, this was part of a bridge we looked at. What I want to show you is, so we had a gap element here, because this is a nonlinear time history analysis. That's the beauty, right? I don't have to iterate in any way. I can just give the nonlinear spring property to the program, and I can say, look, this has a gap of so many mils, and only after that its stiffness kicks in, and then it goes flat at this displacement, and it's just going to find that out for me. So over on this side, I think we had like a standard abutment with gap, so we modeled that. So Hull approach, that's my spring. So you can see SAP has a gap spring that you can use. It's in U1 direction. And I can also give it the, let's just go back here. Okay, so this element, what I'm doing is I give it a stiffness of a certain number. I think what this had was what we were trying to do is, I think the gap was pretty small, but when it moved away, it wouldn't have anything. So my opening is 0. Okay, so it's just basically telling it, look, it's activated right away. So if you have a 25 mil gap, you just put that stiffness, and then you say, my opening is 25 mil. So for the first 25 mils, it's going to have no stiffness active. And then it's going to start to bring that stiffness into it. When you're running a linear analysis, then you need to put some value there. But then that's the only value it's going to work with. It doesn't have the ability to do anything else. We also got some stiffnesses for, this was a pile foundation, but there was a forest of piles. There were about 66 piles. And we didn't want to have 66 piles modeled with their each PY spring. So what we asked the geotech was to do the analysis themselves and come up with an equivalent spring matrix for us that we could use. So they gave us this 6x6 matrix. They mostly had just the diagonal terms, but they found some coupling. Like if you pushed your foundation one way, it might rotate in another degree of freedom. So any of the diagonal terms are basically just, you apply a force this way and the resistance is in the same direction. You apply a force this way, the resistance in the same direction. You apply a moment, there's a rotational restraint. But with some of them, they found that if you activated one degree of freedom, the other degree of freedom got activated. So those are the off diagonal terms. So we got those in there. And then we had the elastomeric bearings. So we gave the property of that, and then this was more of a hysteretic rule. We put multilinear plastic kinematic hysteresis rule there, so that when it's unloading, it's coming down on a different path. So you can model. The only reason I'm showing you this is you can model a lot of these different things. We had caissons there that were very, very stiff. And these are the two caissons. We wanted to make sure that these caissons, they had no reinforcement. They were just big, that these caissons wouldn't just fail. Okay, so now here is the this is how, now the time histories were displacement time histories. They weren't acceleration time histories. And in a lot of the softwares, you can apply acceleration time histories, but when you apply the acceleration time histories, it applies those to every support location. So you can't have multiple support excitation. You can't put one time history here and a different time history there. If you want to do that, you've got to apply a displacement time history. That's certainly the case for CSI bridge. So this thing is a wall. It's got some soil behind it, some soil underneath. So this is just, again, just telling it, this is just like I was talking about the mode shape for the pushover. This is just going to tell the program, look, this is a time history load pattern. You apply a unit there, a unit there. It doesn't mean anything. It's just telling it, this is where you're going to go and apply your time history record in this direction. Okay, so we introduced it there, and then we were trying to study this whole thing. One was longitudinal, I believe. One was transverse. And then what you do is you go in and you tie those. So these are all the time histories. There were piles, and the reason we had piles was because there was a big, deep alluvial deposit up at the abutment level. As you moved away, rock came in. This was in Montreal. So that's why we needed to apply different time histories. One support is seeing time histories that are filtering through a soil medium, and a few meters away, there is rock. It doesn't happen very often, and so you don't need to do this. But in this case, this was happening, and we wanted to capture it. So you see how there is a set H1 pile and rock, pile and rock. So the piles are applied over there. The rock is applied down here. So then you go and you tie. This is just showing you different time histories. So now you have to go and tie these together. So this is like a load case that's going to start from the dead load case. It's going to take the hull abutment X and Y, which is tied to the pile time histories, and then it's going to tie that, the caissons are tied to the rock. Okay, so now you're applying the time history for soil to the pile location and for rock to the caisson location. So within this, you've got X and Y applied at the abutment, and you've got X and Y applied at the caissons, but they're different time histories. Okay. Now in softwares, you can plot some functions. So I'm going to pick an element or a link, and I want to look at its deformation or whatever. So I'm going to plot a function. So you can go in there and say define plot function, and I can get that. You can name it whatever you want, but really I just want to show you that you can take a component. So this is link 22, and it might be one of those soil links or this other link, I forget right now, and I can ask it to plot the axial force at one of its ends. Okay, so it's going to give me the output for the whole time history. So now I've added that. That's my link 22. It's got all that information stored in it. Once I go here, so here's the case. This is the gap element, which has compression-only behavior. So it only activates when the bridge is pushing into the soil. When the earthquake takes it the other way, it just gives you nothing. So you see all the lines are below the zero line. Okay, and so now here you can quickly see that your maximum is 1.35 times 10 to the 3, so about 1,350 kilonewtons. And if that's the force that you're modeling in your soil in the back wall, now you can look at the back wall and see if the back wall has the capacity to take that much. That, of course, you'd have to go and check. But these are the type of things, very powerful things that you can do with a nonlinear time history analysis, whereas response spectrum is not able to capture those. This is the Caisson moment time history, and you can see it jumps from 15, 16,000 down to about -6. Even though these caissons had no rebar, they were just ginormous, so even their cracking was much higher than this. So once we did this, we were fairly comfortable that the caissons weren't going to crack. Okay. I think I'm going to skip the base isolation. Well, I'll just give you a quick 2-minute summary here. And then maybe we'll break for lunch. Yes?
It's the question actually previous slide.
Yeah.
You apply this support excitation. So you apply the acceleration at the support point or the displacement?
Because this software cannot apply different time histories at different supports to acceleration, we asked the geotechnical engineer to give us displacement time histories. Because it's able to apply displacement time histories, different displacement time histories at different.
So with time you apply different displacement at the base.
Yes.
And
Yes.
based on that, so there's no mass nothing. Only the direct displacement.
Yeah, it's a direct displacement of the ground.
And based on that you will calculate the
Exactly. Okay, so why do earthquakes damage structures? It's really the fact that there's a correspondence of the periods of vibration of a structure and the frequency of seismic input. A very classic example was the 85 earthquake of Mexico City, which sits in a big basin. And when you're in that sort of a scenario, as the earthquake waves are coming up, their signature changes and there's a lot of long period energy that comes through. So most of the buildings in Mexico City in 85 that were 1 to 2 stories were just sitting there. No damage, nothing. Now the 20 to 30 story buildings were what had some real damage, because there was resonance. There was that correspondence between the fundamental period of a 20, 30 story building and the energy that was coming through the basin. So a lot of the structures, they're able to avoid that sort of catastrophic failure for different reasons. One could be that you have short period energy, and in a neighborhood you've got these tall buildings, or vice versa. You could have damage because of that. And that's why I'm saying in Victoria, for example, if there's a crustal event which is quite rich in short period, high frequency energies, we've got lots of unreinforced masonry, single story, 2-story buildings. They're going to vibrate at like 0.3 seconds. That, sometimes wakes me up at night. But that's that now. Now think about a 50-story building in Vancouver and Cascadia hits, and that's a 3-second plus building or 4-second plus building where now Cascadia is bringing in a lot of energy. That's what's going to create problems. sometimes what happens is the structures, if they have this ductility capacity as they damage, their stiffness goes down, their fundamental period changes, and they're able to survive the rest of the earthquake. If it's rich in that band, now it's moved out of it, it's not going to keep behaving in a very inelastic manner. It's just going to, the period is going to change, and hopefully something is just not going to, the correspondence is broken between the two. So what we can do is we can artificially increase the structural period and the energy dissipating capacity of a structure. And that's where the concept of base isolation comes in. So the most important part, of course, or the element is the isolation and dissipation devices, and we tend to put them between the deck and the piers. The buildings, you'll see a lot of them are at the base of the columns, and that makes a lot of sense because now all of it is isolated, and the columns are just going to float on top, and the building up there it's going more into a rigid body movement. As long as you can take the displacements, you're okay. In bridges, we tend to put them not between the column and the pier cap. We tend to put them between the pier cap and the superstructure. So now that's where most of the mass is, and that's what moves, and things hopefully just work out. A different scenario arises when you look at a lot of the older bridges with massive wall piers in rivers or otherwise, because now you've got almost the same mass in the substructure as you do in the superstructure. So there, if you isolate, you've only isolated part of the problem. And now if your wall pier is not very ductile, it's stiff as hell, it's really strong, but the earthquake is going to push it to its limit, it might just fall. I visited Pakistan after the big 2005 Kashmir earthquake, and I was looking at a lot of the schools there, and it became very apparent to me very, very quickly that it was the construction that was primarily responsible. But when you look at the construction up in the north, it's very shoddy. These are unreinforced stone masonry walls that are 2 feet wide, and you've got these light wooden trusses sitting on top as the roof, as the roof or the ceiling. Usually, when you think of buildings and bridges, you know that your seismic mass is up there. It's in the floor. It's in the deck. Okay. Now here, all the seismic mass is in this ginormous, big, strong wall with bad mortar and unshaped masonry. It's really bad, and the trusses are just not able to stabilize those things. So these are pretty much freestanding walls. So these walls basically crumbled under their own inertia, and the roofs fell down. It's not that the roofs brought down the walls; it's just that the walls crumbled and killed thousands of children, and that was, quite heartrending. And yeah, okay. So I'll just very quickly. So that's what I'm trying to say is if you've got that sort of a massive pier underneath, you may not have solved the problem completely. You may need to do something with the pier as well. Okay, so these elements may undergo significant plasticity. You've got to make sure that you control your displacement. That's a big thing. So the 3 big conditions, you should have big or stiff piers and a low period of vibration so that you move it, you lengthen it. If you have a lot of irregularity in your system and one is going to get hit more, then you can bring in these devices and you can tune them properly so that you get uniformity of response happening. And your expected motions should be dominant in low period or high frequency energies. Otherwise, you're not going to have too much benefit. You want to stay away from this sort of a situation where you're sitting, somewhere your period is at 0.5 seconds and you're seeing 0.9 G. Now you put these devices, you lengthen the period to 3 seconds, and up comes the next peak in your response spectrum. You've actually increased it. This is not a very typical response spectrum, but a lot of the times you see in actual earthquake response spectra that there is a second and a third kick at longer periods. So you want to be mindful of that. Okay, so that's just it about this. There is a lot of material here that you can go through for seismic base isolation. just remember it's only going to be helpful if you've got most of the mass up top. It's going to be helpful if you've got earthquakes that are rich in high frequency and your structure is short period. So now you want to move away from high frequency to longer period and break that correspondence. So I think we can take a half hour. 1 o'clock we'll start.
Okay, the food is here already, so it's help yourself.
Pretty neat.
Yeah, take off. So I'll see you tomorrow morning.
Okay, yeah, for
Great.
sure.
Thank you.
Okay, thank you very much.
Sure.
Yeah. Take your, he's got, well, he doesn't need it, then please leave.
Oh, you're leaving? Yeah, we can leave. Although you might not need it, but in case you do, yeah.
Thank you, Dr. Al.
So, yeah, we'll talk later then.
Yeah, you bet.
Maybe. I'll be back.
Yeah, yeah. So I think I'll finish at 3.
Yeah.
2 more hours and I'll finish. That'll be exactly 12 hours.
Yeah, I'll be back.
So. So what's about how is life?
Good, good.
Yeah?
I was wondering about the 6 months. Like, would I be able to have a certificate of experience or something?
Yeah, we can do
Like,
that.
signed by you?
Yeah.
In case I want to apply for the PM?
Yeah, yeah. Oh yeah, definitely.
Shall I listen to
You don't need that though. When you put in your application, you describe your experience and you nominate me online
Okay.
to say that he will sign off on it. So then I just sign off on it online.
Oh,
You don't need a certificate.
Oh, so they must just send you an email or something?
They send me an email and they say somebody has requested that you sign off on their experience. It's all electronic now.
Oh,
So just do that
okay.
and I'll be happy to sign off on the 6 month. Yeah. So you just describe what you did, kind of problems you solved, what kind of work you did, and then I'll sign off.
Even though if you change like your company maybe?
Or that doesn't matter.
Like the email doesn't match the company you work for or something?
No, it doesn't matter because if I changed my company, I go into the database, I change my email. So no matter where I go, I get.
Just link your ID, yeah?
Yeah, it's linked. Well, if I were to ever change my job, you go into your profile on EGBC's website and you change your address, even if you move. Yeah. Plus, I do lots of interviews for EGBC and stuff, so they always have my current information, right? Because I'm on the panel for PNG applications and all that. I volunteer with them.
I was wondering if they would count my overseas experience.
They do. They ask you to have at least 1 year of Canadian experience.
So even if the overseas supervisor,
Yeah. He or she has to sign off on it.
oh, okay, like I had 1 year, I was supervised by a PA.
Yeah.
It was a PA in Ontario.
Mhm.
But the other year, I didn't have.
If you don't have the PMs, then it's a problem.
Oh,
It becomes a little gray.
so they'll be sending an email to them.
Whomever you nominate, as many people as you nominate, you give them the info, their emails, and the system sends out the email. Sorry,
No, sorry, I'm just stop that.
it's still going.
Yeah.
I better not start swearing then.